So, welcome to lecture number 39 in our course on fundamentals of transport processes, where we were going through the final topic in our course, and that is transport at high Peclet number, where we expect convective transport to be dominant in comparison to diffusion. If you recall, we had obtained a convection diffusion equation for the concentration and temperature fields, and it was of the form shown here right on top. It has a time derivative dc by dt plus the divergence of velocity times concentration is equal to d times the Laplacian of concentration plus any sources or sinks. If I scale the velocity by a characteristic velocity capital U and length scale by characteristic length L, then I get a scale equation which ends up having a Peclet number in it, ratio of convection and diffusion. Peclet number is UL by D. D of course is a diffusion coefficient which has dimensions of length square per unit time. So, this is dimensionless. In the limit of small Peclet number, the transport is diffusion dominated, and we looked at various ways of solving basically the Laplace equation d del square c is equal to 0 or d del square c plus a distributed source is equal to 0. We looked at various strategies for solving this, including separation of variables as well as the temperature or concentration fields due to point sources and dipoles and so on. And we are on the topic of high Peclet number now. And naively, you might think that in the limit of high Peclet number, I could just completely neglect diffusion altogether and just solve an equation of the form dc by dt plus divergence of u times c is equal to 0. For incompressible flows, basically what this equation will tell me is that the concentration is unchanged along streamlines. We looked at some special cases. First, the flow past a flat plate at steady state, del dot ut is equal to the thermal diffusivity times del square of the temperature. The flow is assumed to be linear at the surface, ux is equal to gamma dot times y, and on this flat surface there is a heated section of length L from x is equal to 0 to x is equal to L, and due to thermal diffusion the energy diffuses from this section into the fluid, and our task was to find out the temperature profile in the fluid. If we just make the assumption that we neglect the diffusion terms altogether, then we just end up with an equation of the form dt by dx is equal to 0. That is, the temperature is invariant along streamlines, and if T is equal to 0 at the inlet, it has to be 0 everywhere. We cannot enforce the boundary conditions at the heated surface in that case, because at the heated surface the temperature has to be equal to 1, the scale temperature. Okay. The problem was that when we neglected the diffusion terms, the equation was converted from a second order differential equation to an ordinary equation. For a second order differential equation in y, there are two boundary conditions. For an ordinary equation, there are none. And since we do not have boundary conditions, we do not have constants in the equations which emerge from the integration of the differential equation, we were unable to satisfy boundary conditions. Physically, the reason was that when I scaled the equation, I implicitly assumed that the length scale for variation of the temperature field is also capital L, because that is the only length scale in the problem. Now, if the length scale is capital L, we got the result that convection is large compared to diffusion, or gamma dot L square by alpha is large compared to 1. That only means that over a length of order capital L, convection is dominant in comparison to diffusion. However, there is still going to be diffusion at the surface, because diffusion is due to the fluctuating motion of the molecules. And as convection becomes larger and larger, the temperature, the energy that is diffusing from the surface gets swept downstream, and therefore, it penetrates only to a small distance within that fluid. And if the distance of penetration is small, the gradient is large, and one could still have a balance between convection and diffusion. So, the way to solve this problem is to postulate a length scale small l in the cross stream direction. Okay, postulate a length scale small l in the cross stream direction, which is the length scale over which there is penetration of the energy disturbance due to the heated wall. And we will determine this length scale small l self consistently from the requirement that convection and diffusion have to be of same magnitude over this length scale small l. So, we went through that scaling exercise, and we finally found out that for this particular case, where the velocity is 0 at the wall and it increases linearly from the wall, this small l divided by capital L is equal to Peclet number power minus 1/3, where Peclet number is based upon the thermal diffusivity and the length capital L. Okay. So, this scaling analysis gave us a penetration depth for the energy disturbance from the wall. Okay. However, that did not give us a solution to the problem. The solution was obtained using a similarity transform, which is similar to what we had used for the instantaneous flow past a flat plate in our very first series of lectures on shell balances. So, the procedures that we are using, similarity solutions, separation of variables, are identical to what we had done for the elementary problems in shell balances, the same approaches we are using for more complicated problems here. So, the similarity postulate was that the length scale of penetration small l at a distance x from the start of the heated section does not depend upon the total length capital L, because we have neglected diffusion in the streamwise direction, and convection only sweeps temperature, the energy disturbances downstream. Okay. So, the length scale at a given distance x can depend only upon x itself, and from that we just got a similarity variable y by L of x is y by alpha x by gamma dot power 1/3. Okay. So, that means that the boundary layer thickness at a distance x from the upstream section goes as x power 1/3. It is increasing as 1/3 power of the distance. And using that, we had got a similarity solution. Okay. The equation that we got was of the form d square t by d eta square is equal to minus eta square times d eta by dt by d eta, and that can be solved quite easily to get a solution for the temperature field, and then a solution for the heat flux, and then a solution for the Nusselt number as a function of the Peclet number. So, that is the Nusselt number correlation for the flow past a flat plate. Okay. We had done the same thing for the flow around a spherical particle. Okay. In that case, we are given a velocity field, okay, for the viscous flow around a spherical particle. This we did not calculate, this is given to us. The calculation of this right now is outside the scope of this course. Okay. But given this velocity field, we followed a similar procedure. Convection is large compared to diffusion. So, if you just simplistically neglect diffusion, the solution you would get is that the temperature is a constant along streamlines. that does not satisfy the boundary conditions at the surface of the sphere. Therefore, one has to postulate a boundary layer of thickness small compared to the radius at the surface. So, therefore, we used a similarity first of all, since the thickness of the boundary layer is small compared to the radius of the particle, we can use an expansion for the velocity fields in terms of the distance from the surface. Okay. We got an expansion for the velocity fields in terms of the distance from the surface, which was labeled as delta y. Delta was a boundary layer thickness, y was the distance from the surface, which is order 1 in the limit as Peclet number goes to infinity. So, in the limit as Peclet number goes to infinity, y continues to be of order 1, while delta scales in some way with Peclet number, and that scaling is found out from the requirement that convection and diffusion have to be of the same magnitude. Okay. So, we found out that the radial velocity u r went as delta square times y square. So, u r was proportional to delta square, while u theta was proportional to delta. Okay. So, we put this all into the equation for the temperature field, and from the requirement that convection and diffusion have to be of the same magnitude, we found that the delta is equal to P e power minus 1/3. Okay. Similar to the scaling for the flow past a flat plate. Okay. And we got a similarity solution by postulating the similarity variable of the form y by h of theta, where h is some function which, when inserted into the equation, results in an equation of the similarity form. So, that is the basic principle. I choose a form for h in such a way that when I put this into the governing equation, I get an equation which is of the similarity form. Okay. If I put this into the governing equation, I should end up with an equation that is of the similarity form. And I showed you how to do that. You express the derivatives with respect to x and y in terms of h, and you will end up with an equation which looks like this at the bottom. Okay. You have eta square dt d eta times something which is a function of theta is equal to d square t by d eta square. And if we are to get a similarity form, all those terms in blue have to be equal to a constant. Okay. These have to be a negative constant if the temperature disturbance is to go to 0 as eta goes to infinity or as y goes to infinity, far from the surface. The specific value of the constant does not really matter. We had seen this before. That is because there is h itself is only a scaling factor. If I change h by a factor of 2, the solution for the temperature field that I get in terms of eta will change, but the temperature field that I get in terms of r will continue to remain the same, because h is only a scaling factor that I have used to scale y. And then you get an equation that is very similar to what we had for the flow past a flat plate. In fact, for any geometry, this equation will be exactly the same up to a constant sitting in front of the second term on the left. Only this constant will change, nothing else will change in this equation depending upon the scaling factor that I have used for the function eta. And the solution ends up being identical to what I get for the flow past a flat plate. Okay. However, we still have to find a solution for h. Okay. And I showed you that the solution for h depends upon the specific is obtained as usual by variation of parameters. And the final solution for h actually has a constant in it. That constant has to be determined from the boundary conditions in theta. Okay. One condition that you have for theta is that the upstream stagnation point at theta is equal to pi or x is equal to minus 1 at the upstream stagnation point, the boundary layer has to be of finite thickness. Note that this solution for h cubed actually goes to infinity at both x is equal to plus 1 and x is equal to minus 1. I have only one constant in this. I can choose that constant to make h cubed finite either at the upstream or the downstream stagnation point. If I choose the constant to make h finite at the upstream stagnation point, then this constant c has to be equal to 0, and I get a solution for h cubed, and this solution, as I showed you, will tell you that the boundary layer thickness h is going to infinity at the downstream stagnation point. Okay. As I explained in the previous lecture, this boundary layer thickness is finite at the upstream stagnation point. Okay. However, as you go downstream, h diverges, it goes to infinity. Okay. H goes to infinity at the downstream stagnation point. That means that you have a wake behind the particle. In order to analyze the temperature field in the wake, it is a more complicated task. One has to do an expansion in the angle theta about theta is equal to 0, and that is not within the scope of this course. Okay. But it turns out that the details of the wake do not really affect the scaling of the Nusselt number with the Peclet number. Okay. The scaling that I get, the dominant contribution to the heat flux from the particle is actually from the entire surface, the entire boundary layer region, and the contribution from the wake is actually small, because the length scale is becoming large in the wake, and therefore the flux is becoming small. Therefore, the contribution to the total heat coming out of the particle is actually small at the downstream wake region, and therefore it is not necessary to calculate the details of the flow in the wake in order of the temperature field in the wake in order to get the Nusselt number versus Peclet number correlation. And I had obtained that correlation for you in that lecture, in the previous lecture, by actually calculating the value of h and then putting that into the heat flux at the surface and integrating that heat flux over the entire surface. Okay, and you end up having to integrate a term that goes as 1 over h of theta times sin theta d theta over the surface. And if you do that, you get that the Nusselt number goes as 1.2491 times p power 1/3, exactly the same scaling as the flow past a flat plate. In fact, as I showed you in the previous lecture, for any object which satisfies the no slip boundary condition at the surface, okay, the tangential velocity has to go to 0 at the surface. If there is a net shear stress, so that the velocity gradient is non-zero, that means that the tangential velocity has to go as y, where y is the distance from the surface. From the mass conservation equation, the normal velocity has to go as y square. Okay. And if you put in these dependencies of y and y square, you will end up with a boundary layer thickness that goes as p power minus 1/3. Okay. If the boundary layer thickness goes as p power minus 1/3, then it is inevitable that the Nusselt number will go as p power plus 1/3. Okay. Only the constant changes. The scaling of the Nusselt number with the Peclet number remains the same. Now, this is one particular case where the velocity goes to 0 at the surface. Okay. Let us consider another case where the velocity itself, the tangential velocity itself, is not 0 at the surface. Okay. Okay. If I have a gas bubble that is moving with a velocity relative to the fluid, okay, then the tangential velocity at the surface of the bubble is not 0, because we do not apply no slip conditions at the surface. Rather, we apply 0 shear stress condition at the surface. Okay. So, for example, if I had a bubble and there was a fluid that was incident on this bubble with a velocity u. Then at the surface of the bubble, provided the bubble is spherical and remains spherical as the flow goes past it, the normal velocity at the surface has to be equal to 0 because the fluid cannot penetrate the bubble. However, the tangential velocity along the surface of the bubble is not 0 because the fluid can have a non-zero tangential velocity along the surface. So, in general there is a 0 shear stress condition, which basically means that the gradient of the velocity has to be 0 at the surface, but the velocity itself does not have to be 0 at the surface. The question is, in this case, what is the relation between the Peclet number and the Nusselt number? We have already solved one such problem where the tangential velocity is non-zero, way back when we looked at unidirectional transport. Okay. If you recall this following film, the following gas film, in this case as well the tangential velocity is non-zero at the surface. Okay. And we did a differential balance. Okay. We assumed that the velocity was a constant at the surface. The assumption basically is that over length scale over which diffusion of mass takes place, the velocity is not changing. And we went back and found out conditions for that case, why the under what conditions can we assume that the velocity is a constant. And using the mass balance condition, we got an equation of this form: u dc by dx is equal to d square c by dz square, and we solved this. Okay. Got a solution that went as e power minus psi square by 4. Okay. And from that we had got a correlation between the Nusselt number and the Peclet number. Okay. And this was the correlation. Okay. This was the correlation for the Sherwood number or the Nusselt number as a function of the Peclet number. Okay. It goes as Peclet number to the half power, in contrast to the 1/3 power that we had for flow past solid surfaces. Okay. This once again is a common feature of all flows where there is slip at the surface, where the tangential velocity at the surface is non-zero. And we will see that that is the solution that you get even for the case where we have flow past a gas bubble. Okay, so let us look at this problem. So, I have a gas bubble here, and I will use this gas bubble has a radius r, and I will use a coordinate system where this is the z coordinate. Okay. So, the distance is r and this is the angle theta, and the fluid is incident with a velocity u on this gas bubble. Okay. Now, the velocity components u r and u theta for this case, this once again is an axisymmetric configuration. There is no dependence on the angle phi around the axis, and the angle and the velocity in that direction, in the phi direction, is identically equal to 0. So, there is no dependence on the phi coordinate in this problem. Okay. One can obtain the velocity components for this particular case. Okay. Once again, right now that is outside the scope of this course because we have not gone through the details of fluid mechanics, but I can write the velocities for you. U r is equal to u cos theta into 1 minus r by r, and u theta is equal to minus u sin theta 1 minus 1 by 2. Sorry. And I should change this. So, these are the two velocity components u r and u theta. Okay. And my convection diffusion equation is u r dt by dr plus u theta by r partial t by partial theta is equal to alpha into and the boundary conditions that I impose on the surface are as usual t is equal to t naught on the surface and t is equal to t infinity as r goes to infinity. So, the temperature is T infinity far from the surface and it is equal to T naught at the surface of the bubble itself. And one would like to find out what is the variation of the temperature field, and from that the heat flux and the Nusselt number. Define scaled variables once again. U r star is equal to u r by u, T star is equal to T minus T infinity by T naught minus T infinity, and r star is equal to r by capital R. Okay. And my conservation equation becomes u r star dt by dr plus the whole thing into a Peclet number. Okay. The whole thing into a Peclet number, okay, is equal to 1 by r square t by dr where P is equal to u r by alpha. Okay. Once again, if you take the limit of high Peclet number, if you were just to neglect the diffusion terms altogether, then the solution you would get is that the temperature is a constant along streamlines. That clearly does not satisfy the boundary condition at the surface of the particle, of the bubble. Okay. So, therefore, one has to postulate a boundary layer of small thickness at the surface in which there is a balance between convection and diffusion. Okay. As the thickness of the boundary layer becomes small, the gradient becomes large and the diffusion in the direction perpendicular to the surface becomes large. And if the thickness is sufficiently small such that the diffusion term balances the convection term, then one has a balance between convection and diffusion, diffusion perpendicular to the surface and convection in both the flow as well as the gradient directions. Okay. So, I will postulate a boundary layer, okay, r star, okay, is equal to 1 plus delta y. Okay. R star is equal to 1 is the surface, r is equal to capital R, okay. R star is equal to 1 is the surface. Therefore, I am focusing on a region close to the surface, 1 plus delta y, okay, a region close to the surface. In this region close to the surface, the assumption here is that y is order 1, okay. In the limit as Peclet number goes to infinity, y continues to be a number that is order 1, whereas delta is the one that is varying with Peclet number. You would expect delta to become smaller and smaller as the Peclet number becomes larger and larger. So, the region over which diffusion takes place becomes smaller as the Peclet number becomes larger. Okay. So, within this region I now need to find out what is the velocities. Okay. I do not need the entire velocity field in terms of r, I just need to know what are the velocities within the small region of order delta. Okay. So, u r star is equal to 1 minus 1 by r star cos theta. Okay. This I can write it as 1 minus 1 by 1 plus delta y cos theta. Okay. And if I use an expansion in the small parameter the delta, this just becomes equal to delta y cos theta. Okay. So, u r is going as delta times y. Okay. U theta is equal to minus of 1 minus 1 by 2 r sin theta is equal to minus of 1 minus 1 by 2 into 1 plus delta y sin theta. Okay. So, this is actually just equal to minus half sin theta. Okay. So, note that in the previous problem for the flow past a particle, u r was proportional to delta times y the whole square and u theta was equal to delta times y. Whereas, in this case u theta is a constant, there is a slip at the surface, okay. There is a relative motion between the fluid and the bubble at the surface, and u r goes as delta times y. Okay. And this is a common feature of all problems where you have a slip at the interface. Okay. So, I insert these two into my equation for the temperature field. Okay. Into delta y cos theta. Okay. dt by dr is 1 over delta partial t by partial y. Okay. Plus minus 1 by 2 sin theta, okay, divided by r, which is 1 plus delta y partial t by partial theta, okay, is equal to 1 by 1 plus delta y the whole square 1 by delta d by dy of 1 plus delta y the whole square 1 by delta partial t by partial y plus okay. So, this is just the convection diffusion equation that I had earlier, that is this particular equation, in which I have substituted r is equal to 1 plus delta y and taken the approximate expressions for u r and u theta. And of course, in this case I can neglect delta y in comparison to 1, because delta is a small parameter. Okay. And once you do that, you will get Peclet number into y cos theta dt by dy minus 1 by 2 sin theta dt by d theta is equal to 1 by delta square partial square t by partial y square plus 1 by sin theta So, note that both terms on the left hand side are of equal magnitude. Okay. They both scale, they are both order 1 in the limit as delta goes to 0. Okay. So, they scale as delta to the power 0 in the limit as delta goes to 0. On the right hand side, I have one term which goes as 1 over delta square, okay, and the other term which has no deltas in front of it. Okay. The cross stream diffusion term goes as 1 over delta square. Okay, the cross stream diffusion term goes as 1 over delta square. This is diffusion in the r coordinate, which is across the flow. The streamwise diffusion term has no deltas in it, and therefore, one can neglect the streamwise diffusion in comparison to the cross stream diffusion. Okay. And once I do that, I will get P times delta square into y cos theta dt by dy minus 1 by 2 sin theta dt by d theta is equal to partial square t by partial y square. Obviously, convection and diffusion are of the same magnitude only if P delta square is 1, which implies that delta is equal to P power minus 1 by 2. Okay. So, that is how you get the Peclet number power minus half scaling for flow past surfaces which have a slip condition, a zero stress condition or a slip condition at the surface. Okay. And once delta is equal to P power minus half, the rest of the equation becomes y cos theta dt by dy minus half sin theta dt by d theta is equal to d square t by dy square. And now I postulate a similarity solution of the form identical to what we had previously. Okay. I postulate a similarity solution of the form identical to what we had previously. Okay. So, I postulate a similarity solution of the form eta is equal to y by h of theta, which means that partial t by partial y is equal to 1 by h partial t by partial eta, okay, by differentiating by chain rule. Partial square t by partial y square is equal to 1 by h square partial square t by partial eta square, and partial t by partial theta is equal to minus y by h square dh by d theta partial t by partial eta is equal to minus eta by h dh by d theta partial t by partial eta. Okay. So, we substitute this into the equation. Okay, substitute this into the equation and we will get into this equation, and we end up with an equation of the form y cos theta, okay, by h partial t by partial eta minus, okay, so I should have a plus here, half sin theta eta by h dh by d theta partial t by partial eta is equal to partial square t by partial eta square. And after some simplifications, I can reduce this to an equation of the form eta times partial t by partial eta into h square cos theta, I should have 1 over h square here, plus half h dh by d theta times sin theta is equal to partial square t by partial eta square. Okay. So, clearly in this problem, to be able to get a solution of the similarity form, this entire term has to be equal to a constant. Okay. To get a similarity form, this entire term has to be a constant. Okay. It also has to be a negative constant because I require the temperature to decay exponentially as distance goes to infinity. Okay, it has to be a negative constant. So, the temperature decays exponentially, okay, as eta goes to infinity or as y goes to infinity. The exact value does not really matter, because if I change h by some factor, the solution in terms of eta is going to change, of course, but the solution that I get in terms of r cannot change, because h is a scaling factor I have used to scale the coordinate. Okay. So, the solution that I get in terms of the radius r will not change, even though the solution in terms of eta will change. So, without loss of generality, I can assume, for example, that h square cos theta plus half h dh by d theta sin theta is equal to minus 2. With this, my equation for the temperature now becomes d square T by d eta square plus two eta times dt by d eta is equal to 0. And I can solve this subject to boundary conditions. Okay. At r star is equal to 1, okay, which means that y is equal to 0, t star has to be equal to 1. Okay. That is the boundary condition at the surface of the bubble. Okay. And as r goes to infinity, y goes to infinity, t star has to be equal to 0. Okay. So, far away t is equal to t infinity, that means that t star is equal to 0. At the surface itself, t star is equal to 1. Okay. In the solution for this equation that satisfies these boundary conditions, you can verify that for yourself. It turns out that this is equal to 1 minus integral 0 to eta d eta prime e power minus eta prime square divided by integral 0 to infinity. Okay. Note that this is different from the solution for the flow past a solid surface. In that case, we had eta cubed, e power minus eta cubed. In this case, we have e power minus eta square. And in fact, this exponential solution will turn out to be the same for any surface at which you have the velocity being non-zero. In fact, if you go back to our earlier example of the flow past of the transport to a falling film. Okay, if you go back to our earlier example of transport to a falling film and look at the solution that we got there, the solution is once again identical. Okay. The similarity variable in that case was psi, and we got e power minus psi square by 4. Okay. Therefore, for any problem where there is a non-zero velocity at the surface, you are going to get a solution that goes as e power minus eta square. Okay. Okay. So, that is for the temperature field in terms of eta. We still have not solved this equation to get h, because eta is equal to y by h, and unless we know what is h, we will not be able to find the solution for the temperature field. The solution for h is obtained the same way as it was for the flow past a spherical particle. Okay. The equation that I have is h square cos theta plus half h dh by d theta sin theta is equal to minus 2. I use the substitution cos theta is equal to x, which implies that dx is equal to sin theta, sorry, minus sin theta. Okay. With this, I will get h square times x minus 1 by 4th into 1 minus x square d h square by dx is equal to minus 2. Okay. Minus 1/4 into 1 minus x square, because the dx is equal to minus sin theta d theta. Okay. Or I have to solve an equation of the form 1 minus x square by 4 d of h square by dx minus h square x is equal to 2. Okay. And this equation one can solve quite easily by variation of parameters. Okay. The solution h square has two parts, which is equal to a general solution times a function that is obtained by variation of parameters. Okay. Where the general solution satisfies the equation 1 minus x square by 4 d of h square g by dx minus h square g times x is equal to 0. And the solution for this can be obtained quite easily. Okay. H square, the general solution, is equal to some constant by 1 minus x square the whole square. The particular function f in this particular case is obtained by substituting h square g into the original equation. Okay. And you can do that, and finally you will get the solution for f is equal to 8 times x. Okay. So, the final solution for h square g for h square is of the form c by 1 minus x square the whole square plus 8x by 1 minus x square. Okay. Now, this function once again h square goes to infinity at x is equal to plus or minus 1. X is plus 1 is the downstream stagnation point. Okay. X is plus 1 corresponds to theta is equal to 0, that is the downstream stagnation point. Okay. X is equal to plus 1. X is equal to minus 1 is the upstream stagnation point. X is equal to minus 1 is the upstream stagnation point, and x is equal to plus 1 is the downstream stagnation point. The solution diverges at both x is equal to minus 1 and x is equal to plus 1. However, I have an unknown constant here. I have a constant c. Okay. And I can choose the constant c in such a way that the solution does not diverge at one of the two stagnation points. Okay. If I choose my constant c such that the solution is of the form h square, okay, h is equal to 8 into 1 plus x by 1 minus x square, okay, by an appropriate choice of the constant c, then the solution does not diverge at the upstream stagnation point, it does diverge at the downstream stagnation point. Okay. So, by appropriate choice of this constant, I can make sure that the solution is finite, that the modular thickness is finite at the upstream stagnation point, which means that it goes something like this. Okay. It does diverge at the downstream stagnation point, okay, resulting in the formation of a wake, as in the case of flow past a spherical particle. In this case as well, h goes to infinity at x is equal to plus 1 if I choose my constant in such a way that h is finite at x is equal to minus 1. And in the downstream stagnation point, h goes to infinity. Of course, our analysis is valid only when delta is small. So, as delta becomes large, our analysis is no longer valid. Therefore, we need to do a different analysis in the limit of small theta in order to capture the details of what is happening in the wake region. Okay. But as in the case of heat transfer from a solid particle, the heat flux in this wake region is actually small. The distance is large, therefore, the gradient is small and the heat flux is small. So, I do not really need to evaluate the details of the temperature field in the downstream wake in order to find out what is the heat flux, because the contribution there is actually small. Okay. So, this basically determines the solution for H h of theta, okay, which is equal to h of cos theta. Okay. Now, I can determine the Nusselt number relation as usual. Okay. The heat flux radially outwards Qr is equal to minus k dt by dr, okay, which is equal to minus k into T naught minus T infinity by r partial T star by partial r star. Write r star in terms of delta and y. So, this becomes minus k into T naught minus T infinity by r delta partial T by partial y. Okay. Change variables from y to eta. Okay. So, this is equal to minus k T naught minus T infinity by r delta times h of theta into partial T by partial eta. Okay. The heat flux at the surface Qr at r is equal to capital R will be equal to minus k into T naught minus T infinity by r delta h of theta times dt by d eta at eta is equal to 0, okay, at the surface itself. And this we have evaluated. Okay. If you go back to our earlier expression for T star, okay, in terms of eta, this we have an expression for T star in terms of eta. So, I can use that expression to write this as minus k T naught minus T infinity by r delta h of theta, okay, times 1 by integral 0 to infinity d eta prime e power minus eta prime square. Okay, this is the derivative of T star with respect to eta. Okay. The total heat Q is equal to 2 pi r square integral from 0 to pi sin theta d theta times qr of theta. Okay. So, if I know what is the form of h of theta, then I can evaluate this total heat coming out exactly. Okay. If I know what is the form of h of theta, I can evaluate the total heat that is coming out exactly. Okay. And from that I can find out the Nusselt number correlation. Okay. Okay, from that I can find out the Nusselt number correlation. Okay. 2q by 4 pi r square T naught minus T infinity by r. Okay. So, I will not go through the details, but if you actually do the entire calculation, okay, what you will get in the end is that the Nusselt number is equal to a constant Peclet number per plus half. That Peclet number per plus half scaling emerges because I have a delta in the denominator here. Delta is equal to p power minus half, okay, and I have delta in the denominator. The rest of the terms are all constants. Okay. So, because of that I get Nusselt number going as p Peclet number power plus half. So, this is the relation between the Nusselt number and the Peclet number for the flow past objects where there is there is a slip condition, where there is a non-zero tangential velocity at the surface. Okay. And this once again is a relation that is valid for any shape of object. Okay. I will just briefly go through the analogy for the case where there is a slip at the surface. Okay. If there is a slip at the surface, then ux is non-zero at the surface. Okay. So, I will just write down the relation for the case where there is a slip at the surface. Slip at surface, ux will be equal to capital U at the surface. There is a slip velocity. Okay. So, ux will be non-zero. Okay. And what that would imply from the incompressibility condition is that uy will be equal to y times delta at the surface. Okay. Okay. The perpendicular velocity will go as u times delta times y. Okay. In contrast to the delta y and delta y square scaling here, you will get 1 and delta y here. Okay. And if you put this into this equation, okay, in this case I have y delta and y square delta square here, whereas when there is a slip there will be 1 and delta y here. Okay. And with that I will straight away get delta by L goes as p power minus 1 by 2. Okay. So, the form of the solution, the form of the similarity variable h of theta in terms of theta or delta of or g of x in terms of x will change, but the scaling ends up remaining the same. And that is why you get a scaling of order of the type Nusselt number goes as Peckley number power half for all problems where there is convection dominant and there is a non-zero velocity at the surface. So, to summarize everything that we have done in this series of lectures on high Peckley number transport, when the Peckley number is large, convection is large compared to diffusion. However, very near the surface there is a region over which diffusion is still important, because convection cannot transport material from the surface to the fluid, because there is no velocity perpendicular to the surface. Thickness of that region is determined by a balance between convection and diffusion by postulating a length scale within that region over which diffusion is comparable to convection. The thickness of that region goes as p power minus 1/3 when there is a no slip condition at the surface. It goes as p power plus minus half when the velocity is non-zero at the surface. From that straight away the Nusselt number goes as p power plus 1/3 when there is no slip condition at the surface, goes as plus half when there is a slip at the surface. The coefficients in the Nusselt number versus Peckley number correlations can be determined by doing boundary layer theory and similarity solutions. In the case of flat plate, the similarity solution is quite straightforward for parallel flows. For flows past objects, there is actually a boundary layer, a wake at the back where the boundary layer thickness goes to infinity. We did not go through the details of the flow in the wake. Suffice to say that the transport in the wake does not really affect the scaling, because the heat flux in the wake region is small compared to the heat flux everywhere else. And that is a brief summary of high Peckley number transport. So, we will briefly summarize everything we have done so far in the next lecture, and we will conclude. We will see you then.